All right, let's get right into it. Today, we're talking about a brand new method for high-dimensional compression called TurboQuant. And believe me, this thing tackles a huge, and I mean foundational problem right at the core of today's large language models. And the best part? It does it by going all the way back to the first principles of information theory. For the longest time, everyone thought the big bottleneck for AI was the compute wall, just not having enough raw processing power. But it turns out the real crisis, especially when LLMs are generating text, is the memory wall. See, as a model like GPT writes, its KV cache, basically its short-term memory, just keeps getting bigger and bigger. So what happens? Your super powerful GPU just ends up sitting there waiting for data to get shuttled back and forth from memory. The mission is crystal clear. We have to compress this data, and we have to do it without messing up the attention scores that actually make these models so smart. So okay, that's the problem we need to solve. But to do it right, you can't just throw a bunch of clever tricks at it. You have to ask a much deeper question. If we're going to be compressing information, what's the absolute laws of physics limit? What is the speed of light for data compression? To answer that question, we have to travel back in time, all the way back to 1948, and the father of information theory himself, Claude Shannon. We're about to go on a bit of a scientific journey, and our first stop is to understand the fundamental law that underpins all data compression. The field we're playing in is called vector quantization, or VQ. Now, it sounds complicated, but the core idea is pretty straightforward. You take a high-dimensional vector, just think of it as a point in a space with thousands of dimensions, and your job is to represent it with a much, much smaller string of bits. The whole game is to get the most compression you can with the least amount of error, or what the experts call distortion. And that brings us to this graph. This is one of the most important charts in the whole field. It's a picture of Shannon's theorem. On the bottom, you have the bit width, basically how much you're compressing. And on the side, you have the expected error. Now that red line, that's Shannon's lower bound. It's the theoretical speed of light for compression. It is physically impossible to build an algorithm that lives in that gray impossible zone. So the holy grail, the absolute dream for any compression algorithm, is to get its performance curve to just hug that red line as tightly as humanly possible. So you have to wonder, right? If we have this beautiful, perfect target to aim for, why has it been so hard to hit? Well, it turns out there's a really subtle, almost invisible flaw in the geometry of how most compression methods work. A flaw that becomes absolutely catastrophic inside an LLM's attention mechanism. Okay, just look at this diagram. You've got an original vector, x, and another one, y. Now, inside an LLM, what really matters isn't just where they are, but the angle between them. That's what attention is all about. But most quantizers, they just try to find the closest possible point, which we call XMSE. They're trying to minimize the simple distance, the mean squared error. And you can see right there, in doing that, they've accidentally changed the angle. The point is closer, sure, but the angular relationship, the thing that actually matters, is now wrong. So here's the kicker. The algorithm thinks it's doing a great job finding the closest point, but what it's actually doing is introducing a tiny systematic error in the angle. Now, for a lot of things, who cares, right? A tiny error. But in a transformer, these values get fed into an exponential softmax function, and that function acts like a giant amplifier for tiny mistakes. It takes this microscopic geometric error and blows it up into a massive retrieval failure, causing the whole model to pay attention to completely the wrong things. So how in the world do you fix a problem that's baked into the very geometry of the approach? You can't just patch it. You need a truly elegant weapon. You need an architecture that's built from the ground up to hunt down and neutralize this inner product bias. So let's meet TurboQuant. At its heart, TurboQuant is a brilliant two-stage pipeline. Stage 1 does what most compressors do. It finds the closest point to minimize distance. But, as we now know, this creates a bias. So, it then calculates the error from that step, the residual, and passes that error to Stage 2. And Stage 2 has only one job in life, to use that residual information to perfectly correct the bias from Stage 1. The result is a single, unified, and totally unbiased estimate. Okay. So that's the big picture. But now we get to the really cool part. We're going to pop the hood and deconstruct this machine because the mathematical principles that make each stage tick are just beautiful. Stage 1 kicks off with a move of pure mathematical genius. It takes whatever data you give it, doesn't matter what it looks like, and applies a random rotation. Why would you do that? Well, it takes advantage of a wild property of high-dimensional space called measure concentration. Basically, if you randomly spin a vector in a space with thousands of dimensions, its coordinates all start to clump together in a very predictable way. They form a nice, clean beta distribution, which, for all intents and purposes, is just a perfect bell curve. It's a way to take any messy, chaotic input and make it orderly and predictable. And because we've now forced all our data into that perfect bell curve, we can do all the hard work ahead of time. We use a classic technique to pre-compute the ideal bins, or centroids, for that specific distribution. So when the actual data comes in, the process is lightning fast. You just take each coordinate and snap it to the nearest pre-computed bin. And bam, that gives you your distance optimized, your MSE optimal result. And now we've arrived at the most critical insight of this whole paper. The difference between the original vector x and the output from stage 1, x_MSE, is this tiny little leftover vector r. Most other methods just throw this away. They assume it's just random noise. But the TurboQuant authors realized this tiny vector isn't noise at all. It contains the entire story of that lethal inner product bias. Throwing it away is the original sin of every biased quantizier out there. So what do you do with this precious little error vector? Stage 2 uses something called a 1-bit quantized Johnson-Lindenstrass transform. Yeah, it's a mouthful. Just think of it as a magic trick. It's a special tool that can capture the essential information of that residual vector using only a single bit per dimension. And here's the magic. It then re-injects that information back into the final estimate, and in doing so, it miraculously preserves the correct angle and perfectly cancels out the bias from stage 1. And the best part? It does this with zero memory overhead. No extra files or numbers to store. It's just pure math. So, we've just walked through this incredibly clever two-stage mathematical engine. The theory is airtight. The logic is beautiful. But does it actually work? Let's look at the proof. And here we are, full circle, back at the Shannon limit graph. And just look at that. That blue line, TurboQuant, is practically painted on top of the red line, the theoretical limit. It achieves an error that's within a constant factor, about 2.7 times, of the physical limit of information itself. I mean, from a theoretical standpoint, this is about as close to perfect as you can get. So how does it stack up against the competition? Well, the comparison is pretty stark. You look at other methods, they're suboptimal, TurboQuant is near optimal. They're biased, TurboQuant is unbiased. They need extra memory overhead for scales and 0 points, TurboQuant needs 0. And it's data oblivious, which means you don't need to spend ages tuning it. Plus, it's designed to run natively on a GPU. Across every metric that matters for modern AI, it's just in a class of its own. And this isn't just theory. This mathematical superiority translates directly into real-world performance. On the left, you've got the famous needle in a haystack test. Can a model find one specific fact in a huge sea of text? TurboQuant gets 100% recall. Perfect score. Other methods start to fail. On the right, for massive vector search, it delivers a 5-fold drop in peak memory use with basically 0 added latency. The math? It really works. So if we're going to boil it all down, TurboQuant's incredible success really comes from 3 pillars. First, it's designed from first principles, going back to Shannon to really solve the problem correctly. Second, it's a zero overhead architecture, using that amazing 1-bit trick to fix the bias for free. And third, it's built for modern hardware, ready to take full advantage of the power of today's GPUs. I'm just going to leave you with this final, powerful quote from the researchers themselves. They make it really clear, this is not just another clever approximation. By proving it's near optimal against the Shannon limit, TurboQuant sets a new, definitive, mathematically proven baseline for the entire field. It fundamentally changes how we should think about solving this problem. So the real question is, what happens next, now that the theoretical speed limit is finally within our grasp?